So now that we went through the whole feature engineering pipeline, we're left with a bunch of artifacts that we have to maintain as though our life depends on it, right? Essentially what we've generated is a feature store that we can persist, let's say, in our local environment. So we can run this to have access to the data, and we will see that our feature store is just a bunch of cleaned features that we're going to be using for our model development pipeline at a later stage. So we could definitely keep this data in our local environment, which is great, but it's not going to be very manageable for a long time. We definitely want to keep this data in a much more safe environment. And all of the code that we have generated so far is kind of like the same story here. We could keep this code, let's say, in this notebook and go back to this notebook whenever we want to run things. But what we definitely want to do is we want to take this code, refactor it, make sure that it's in a clean, understandable state, and then keep it not in our local repository like we do, but really push it into GitHub, where our code should live and be version controlled and be happy, with other scripts and lines of code. So that's precisely what we're concerned with the upcoming labs that we have. So the first lab that you're going to have access to is a GitHub lab that's going to tell you how to take your code and push it onto GitHub. The second lab that you're going to have access to is the BigQuery lab that's going to tell us how to take our feature store, put it on BigQuery, and do some very advanced analytics with this data. And then the third lab that we're going to have is a lab on best practice data, best practice tools that we are going to be using so that we can precisely do the refactoring that happened behind the scene, that took the code from the notebook into the script. So let's get cracking. First of all, the GitHub lab is pretty straightforward, so this one I'm not going to spend too much time on. Well, actually, I'm not going to spend any time on it because all of this is described very neatly in the lab. So we're going to jump quickly over to our first lab, which is Google BigQuery. And what you're going to learn in this lab is you're going to learn to, pretty much what it says here, connect your data to the data warehouse and do a bunch of data-driven analytics so that you can take better decisions. So if you follow the lab, basically quickly you're going to head over to this product here called BigQuery, which is part of the standard product of Google Cloud. If you've set up, if you went the pre-course and you set up your Google Cloud account, then it should be pretty straightforward. You should directly have access to this thing here. And following the lab, you're going to create basically a space where you can create a new table called .feature, and inside of this table, a new data set that is going to be queryable from Google BigQuery. And you will see that this data set basically contains, once you've loaded basically your local data, your data set on BigQuery is just going to contain all of the data that we've just generated ourselves. And because this is just a data warehouse environment, we have the convenience of being able to query it without too much trouble. We should be able to do something like this, a SQL querying on top of this data so that we can visualize the data that we have. This is the power of storing your data as a feature store on a data warehouse. It's that in the same environment where you store the data, you can quickly apply some analytics on top of it so that you can see what you're dealing with. And so we're just going to run this query here, which is just plain SQL statement. Just select all of my data from the feature store that I've just created into this data set, and just make sure that you limit the processing that you apply. Grab the first 1,000 rows instead of reading the 500,000 rows that we have, because BigQuery, it's obviously a paid service, so you pay basically for the processing that you apply on your data. And so the more processing you apply, so for instance, running a query on all of your data, the more processing you apply, the more expensive it's going to be for you at the end of the month. So we're just going to reduce the amount of processing we do. And we see that the preview of our data here shows us that we have exactly what we would expect. In fact, the first row that we have here is the data that we have in our local repository. Well, actually, it's not the same first row because maybe the order of the rows are different. But essentially what we should have is all of the data that we wanted to have access to. So we find that we have the 400,000 rows that we wanted. Why don't we have the 500,000 rows that we had initially when we had the raw data? Well, this is because we rebalanced our data. Remember, we got rid of a lot of oversampled data and we rebalanced it, and so overall we have fewer data than the 500 data points that we had at the beginning. And so, well, obviously we don't have any execution graph, like we don't have any processing applied besides just grabbing the data. If we were doing some more advanced querying, like some group by and things like this, for instance, count, and then some kind of like group by contract. All right, so we see that we have a lot of samples that are coming from the two-tattoo. This is what we saw in the notebook in the previous module, where we had quite a few more samples that were coming from two-tattoo and fewer samples coming from clubs. But essentially now what we can see is the way that this query was processed. So we can see that first of all, what we did is we did like a pretty straightforward querying of all of the rows that there is in the data set. And then finally what we did is some kind of like aggregation on top of this data here. It didn't take quite a lot of time to do it, and the output that we get from this query was pretty straightforward. Like it was very fast, and it's basically what we were saying here in the results. So now we have this environment where we can store our data, we can do a bit of querying on top of it, but it's still not the most convenient way to visualize our data, right? It's still like querying is fine, especially like if you want to do analytics, but if you want to do things like see which kind of features already seems to have predictive power to know whether we're going to win or lose the game, then what we want to do is a bit of kind of like visualization and graphing and plotting of our data. Because if we see that, I don't know, if we see that we consistently have a higher reward, like a higher reward value, whenever we have more jacks or whenever we have, I don't know, like more points at Belote Rebelote, then if we see that visually, we're going to quickly come to the conclusion that this feature is going to be pretty important for us to use. And so to be able to do that precisely, we don't really want to do querying. What we want to do is we want to go into a visualization environment, right? And this visualization environment is exactly what we can do in Sheets, in Google Sheets. We can explore our data with Sheets, where we're going to be able to do a bunch of graphs and things like this. So now I'm going to go over to Sheets and show you what that looks like. So now we launched the sheet thing that's basically connected to our feature store, and we're going to generate some insights directly from our feature store. And all of the querying that is needed to be able to generate this insight is basically completely abstracted away from us, right? Because this Google Sheet is connected on top of our Belote feature store. And so the insights that we're going to generate here are completely, let's say, automatized for us. So whenever we want to create like a new graph, for instance, whenever we come here and create a new graph that's going to show us, for instance, how do the points, like how do the average number of points that I win basically depend on the starting hands that I have? Well, we're going to be placing our features inside of our graph so that we can plot it properly, and we're going to get out of it a query that's going to be run in the background, and that's going to show us the data that we want to see. So if you're familiar with the way that typical intelligence software like Tableau and, well, even Google Sheets work, then you should be pretty accustomed to do this kind of stuff. But yeah, essentially what you're going to have to do in this lab, let's say, to be able to complete it, is to run a few interesting things, like what is the average number of points that I get when I have specific A and D's points, what is the average reward that I get when I have an initial amount of cards in a specific suit. So all of this stuff is things that we can generate at scale and that we can generate in a convenient way, right? So this is exactly what the lab is going to be helping you to do, and I hope that you enjoy it. Now, the final part of the lab that you're going to have access to is this practice tool. And here, it's pretty important to understand like what best practice tools are good for and are not good for. They're very good for harmonizing, let's say, the way that people write code in a certain team, right? So they're very good at telling you like, hey, we should maybe align our way of writing code in that way. if we want to move forward with this project. But they're pretty bad at telling you what is the ultimate best way to do things, right? Except for pretty obvious things like respecting some of the Python standard, let's say, principles. They're usually pretty bad at telling you what is the most optimal way to write code. But if you already, take a stab at implementing them, then you're already like on the path toward writing better, more productized code. And so the three main tools that we are gonna look at today together is Black, PyLint, and MyPy. And we're gonna wrap up with something called profilers, which is not really like, let's say, it's a bit different from the other tools. You're gonna understand why. So if you follow the lab, basically what you're gonna do is you're gonna head over to this file here called best practice. And in this file, in this best practice, we will see that there is a bunch of code and it's written in a pretty poor way, right? We can already see that our PyCharm environment just screams everywhere. Just screams and tells us that things are not how they're supposed to be looking at if you were to write Python code. And instead of going in here and manually fixing everything that we see, right, like giving the white space that we need and the things like that, what we're going to do is we're going to use precisely the tools that we're talking about here to improve what we're doing. And so, to give you an example, we're going to start from here and we're going to use Black to, first of all, reformat the code. And so if I come here and I launch the Black MLOps best practice thing, I can see that Black is taking care of a lot of the reformatting that I need, putting the white space where it needs to be put, getting rid of parentheses that were completely useless, making sure that the whole thing is much more readable. Black is going to automate this whole thing, and that allows us to focus on the second part of this, the linting facility, right? So here there's a bunch of, not bugs, but a bunch of suboptimal way to write Python codes that are not compliant with the way that Python was initially intended to be written, right? So that's why PyLint basically exists. PyLint is a good reminder of how things were meant to be written when we talk about Python. If I come here and I apply PyLint, we will see that, first of all, nothing happens. And this is because we are telling the file right now to skip this file. And that was a small hack so that I could commit it on GitHub. But we're going to remove this from here, and we're going to run PyLint. And we're going to see that PyLint basically tells us that there's a lot of inconsistency and a lot of things that is not working properly with our code as it currently stands. So now we're going to try to improve our code from this aggressively low rating that PyLint is giving us towards a better, let's say, better rating, right? So we're going to go and implement the changes that they're telling us to implement so that we improve things. And finally, the last thing that we want to try is we want to try to improve our typing. Python is not a typed language. It's pretty dynamic. We can do anything we want. We can implement like polymorphism and things like this. So with great flexibility comes a lot of risk of having, let's say, like mistakes and code leaks and stuff like this. But what we want to do is, even though it's not necessarily, we want to make our script a little bit more static, a little bit more types, so that at least we give some indications to our co-workers and our like future self, what kind of input function expect and what kind of output they produce, right? If you have this typing, you help people understand what exactly your code is supposed to be doing. If we run MyPy on this script, what we currently have is just a bunch of like warnings and screamings and errors telling us like, hey, you're creating incompatible types between like a string and an integer and things like this. So again, like just like we did for PyLint, what we need to do here is we need to go in there and implement the changes that MyPy is telling us to implement. And so some of these changes are, for instance, like what we see here on line 51, which is, you have incompatible types in assignment. You start by defining a variable that is an integer, right? Like you say, okay, this function here is going to receive an input and it's going to be an integer and everything is going to be okay if it stays an integer. And then suddenly, after you do a bit of processing on it, and the processing is very irrelevant, it's very dumb, but after you do a bit of processing on it, you end up converting your variable from an integer to a string, and then you return this value as a string. Now, if you come from like Java or like more kind of like static languages, your eyes are completely screaming right now because they're basically like exposed to the crazy nature of Python and the weirdness that comes from having things completely dynamic. But essentially, what MyPy is telling us is that, you know, if you've said that x was going to be an integer, just make sure that it stays an integer, like at least for the time that it's being scoped into this function. And so maybe instead of returning a string, maybe what we want to return here is an integer. And if we really want to return a string, which is fine, then maybe instead of reassigning a new value to x and changing the data type, maybe we should just like make it much more explicit and changing this new variable to y, so that y becomes this new variable that we provide, and you know there is no confusion behind the scene of what happened to x throughout the process of being put in this processing unit. And so that's the kind of stuff that you're going to be doing with MyPy, right? Like you're going to be checking the consistency of your code at a type level, so to say. And finally, like the last piece of processing or like the last piece of code tooling that we're going to do is we're going to profile our code. We're going to see like where is it that we have good code, let's say, well-performing code, and where is it that we have code that could definitely be improved. And the way to do that is by looking with a profiler, but by looking at what part of my code are taking a lot of time to run. Maybe because they just take a lot of time to run once, or maybe because they're just being called a lot. They're just being consistently called, and every small bit of processing adds up to a long time of running. So to be able to do that, we're going to run this line of code here, Python profile. And well, actually, we're going to do this here. We're going to get rid of that. Or actually, you know what's a better way to do that would be to go out of my current folder and to respect the lab. And so what we're doing here when we're launching this profile is we're essentially just running the script, right? Like we're just running the script, which is a pretty straightforward script. It just picks like a random value and then it runs some processing on this value and then gets something out of this, and you know, and that's the value that you see here. Now, the only thing is that it runs this not in a normal way, but really like recording every processing that happens in this file so that we can precisely go deep down into our code and see what part of the code we're taking a long time to run. That's what we're going to do now with the profiler. So that's what this file is for. So if you go into this file here, profiler.py, what you see in there is, first of all, like a first line of code that gets this, let's say, binary data where we have recorded all of the processing that happened in our file of interest. So we get that data in here, we compile it, and then we start looking into each of these processing and we start like ordering them in terms of how much time they took to run, right? And then we can like print that to the terminal so that we can see which part of our code were crazy to run. So we're going to run this guy here, Python MLOps profiler. And we're going to see that our profiler, like if we go up, and we can make this a little bit bigger, we're going to see that our profiler tells us like you essentially like run this stuff here in a very low amount of time. But one of the part of your script that has just been run was called a few times. It was called like 3 times. And compared to the next functional unit, it took a huge amount of time to run. It took like 3 seconds to run. And if you look at the cumulative time, basically, it's also like 3 seconds. And it tells you that essentially this function here that was running in that amount of time was this kind of like time.sleep, right? So now you can go back to your script and you can say like, hey, did I actually write somewhere that my program should sleep at some point? And so if we go here and we look at our program, there is this kind of like function called buffer, right? And this buffer here is implemented in our processing unit, and this buffer is called for every value that's in here. And this buffer is exactly what's causing my program to run very slowly, because if this buffer was not implemented, then I would have the same runtime minus 3 seconds that it took to run the buffer. And obviously this is a very dumb and useless example, right? But what I want to show you here is the process, like the thinking that is put behind improving your efficiency of your code, which is, run your profiling so that you see where is thing taking time, and if you identify the source of the code, the bottleneck in your code, then you get rid of it or improve by writing it more efficiently and things like that. So this is exactly what the profiling wants to help you with. And so all in all, if you have gone through this lab, then what you get out of this is a much more clean script that allows you to, not just refactor very dumb and illustratory script like this one, but much more advanced script like the feature script that we had from the beginning. And this is exactly the technique that I use to make this much more efficient and much more easy to read, let's say. So take the time to go through the labs. I hope that you enjoy them, and see you soon.